Hello again. I think now we ought to talk a little more about Chapter 6 and regression. We had a bit of an introduction to this topic last week, but let's talk some more. Of course, the first thing that you learn about regression would be how can you predict some variable y using some other variable x. And sometimes the linear model would be written as y equal beta 0 plus beta 1 x. And this is the simplest linear model. And in this model, we call it a linear model because the xy pairs would describe a straight line, and the beta naught would be the intercept, or where that line crosses the vertical axis, and the beta 1 would be the slope. But we can go much beyond this and get better and better models. And that's what we want to talk about today. So a much more general model would be, can you read that? More general model. Something like this: predict y with features from your data set, and let's just call them x1, x2, and xk, where the model is going to look like y is equal to an intercept plus sigma I equal 1 to k, because we're using k features here. So this would be the intercept, and I equal 1 to k beta I xi. And this much would be the approximation, and the epsilon would be the error term. Now, a popular notation that you'll see a lot of places and in our text for sure would be if we would let x0 equal 1, and let's call our alpha a beta 0. Not a substantial change, but now we can write our model as y is equal to sigma, and this would be I equals 0 to the number of features we're using, beta I xi plus an epsilon. And the whole activity of linear regression is to find the beta i's and minimize the error. And we'll be using, of course, a least squared algorithm for minimizing error. Okay. Now, reading your textbook, and you know by now I'm a big fan of this textbook, the statement is made very eloquently that the most used data mining technique is regression. But regression has a couple nuances that make it a bit different from other algorithms that we've looked at. In other algorithms, we kind of train the data set, and the data set itself then, with the algorithm, determine what the model was going to look like. Here the user picks the features used in the regression. So that's going to be a user responsibility now. Well, not too difficult because we have some very nice tools to help us do that. But we have to operate the tools. So let's look at I'm checking my notes here. I think we're ready to go take a look. We are at some R code and see how all this comes together. Now I'm going to pull my R screen over here and try to line this up optimally for you. I think that's pretty good. And on line 248, I'm loading up, or I have just loaded, a set of data that we've seen before. The data is called New Body, and it's 300 observations of 15 variables. And you'll remember what the variables look like. They look like age, gender, pulse. So after gender starts a series of kind of blood chemistry things. The pulse rate, the systolic and diastolic blood pressure, the lipoprotein measures, high and low density, the white blood cells, red blood cells, and platelet counts. So that's sort of one subset right there of the data in this data frame. Now, body measures are the rest of the data features here. So we've got weight and height, the waist measurement, the arm circumference, and the body mass index. So that's the data set that I want to be playing with. I like it because it's got a nice set of features. They're numeric, and we've got 300 observations, and so I'm really sort of tired of working with data sets that have 20 or 30 observations, not enough information. So nice data set. So somewhere around line 248, I've loaded this data set. Now actually, you know how I've done this. Why doesn't it show in the script? I should have put it in the script, but the way I did it was to put it into my working directory, and here it is right here, new body, comma separated variable file. It's in my working directory, and then I did an import data set, and it landed in my global environment right here. So now I've got a data set. And my goal is going to be to predict a person's weight. That's what I want to predict. Now let's see what we've got to work with, because remember, in linear regression, it's up to us to build the model. And so I'm going to run names, and these are the names I just went over, but I'm illustrating the commands and kind of a useful sequence for going through these commands. When I see my features here, my variables, I want to predict weight, and my supposition right now is that probably pulse is not going to help me predict weight, and neither is the blood chemistry of high density and low density lipoproteins. I'm more apt to get help predicting weight from variables like height, waist, arm circumference, and BMI. I'm going to be reluctant to try to predict weight using height and BMI both, because these are related variables. BMI is defined in terms of functions of weight and height. And so I probably will use one or the other, but not both. Now, how do I decide if I'm going to create a model here? How do I decide what variables would be appropriate variables to use? Well, one way is to look at the correlation between two variables. Now, the correlation is a measure of the tendency of the variables to vary together, which would mean that the variables are related, which would mean that I might be able to use one to predict the other, which is what regression is about. So in line 253, I'm going to do a correlation between the arm circumference and weight. And let's see what that looks like. Well, we've got a correlation of 0.89. And that's pretty high, especially when I've got 300 pairs. So it looks like arm circumference would have some real power as far as predicting what a person's weight was. And just to do it again, I've got in line 254, I'm going to calculate the correlation between weight and the waist measurement. And so if we run that, we see that I've got a correlation of even more, 0.8945. So even more correlation. So boy, both arm circumference and weight look like they are pretty good predictors. I just said that wrong. Arm circumference and waist measurement, the distance around, are pretty good predictors of weight. So we've learned something already. Now, we can fiddle around here with variables that we think might be good predictors and measure the circumference one at a time. But there are a couple tools that are available to us in R that make that job much easier. Now, I've loaded a folder I want to show you called Psych. And here it is. I'd already installed it, so all I had to do was pull it out of the library. And it doesn't show here because I used the tools in RStudio. But PSYCH is the package, and it came from the archive. If you don't have it already, I think many of you do, but if you don't have it already, you can get it. And you know they're free, no problems. So I loaded that, and in that is a procedure called pairs.panels. Now, native to R, that is in base R, there's a procedure called pairs that does something similar. But by loading the package and looking at pairs.panel, I get some extra bells and whistles that I really like. So when would it be appropriate to use this? Well, when I'm looking at my data and exploring the data and getting to know the data, and I'm looking for predictors of one of the values in my data frame, in this case weight. This is the syntax. You've got to name your data frame, and that is new body is what I've loaded it as. And I want all the rows, but in the columns I want the weight and the arm circumference and the height and the waist. Weight is what I want to predict, and these are what I think are maybe likely predictors, intuition guiding that. And then I'm going to put a title on it, and the title is Find Predictors. So why don't we do that? And this is the output, and I want to blow it up. So let me haul it over here. And I want to get it appropriate size. That looks pretty good. So this is the output. And this is a nicely complex output. You can see the variables I called for: weight, arm circumference, height, and waist down the main diagonal. And these are histograms of the individual values. And this is plotted as a histogram. And then the continuous curve is a density plot over the histogram. And so, I mean, what do you see here? Well, I see something that is sort of normal, but it's a little bit skewed right. And arm circumference, again, I would call this a little bit skewed right, but there's my histogram. Height, that one actually looks pretty normal. And waist, again, a little bit skewed right. But that's not what we came to talk about, but these are our variables that we're looking at. Now, in the upper triangle, I have the correlations of one of these variables with the other. For example, this 0.89 is a correlation between the row would be weight, and the column would be arm circumference. So it looks like there's a strong relationship between arm circumference and weight. Now this one we already know because we looked at it individually a while ago. Between height and weight, we got a correlation of 0.36. Not as strong as I thought. Between height and arm circumference, a correlation of 0.18. That's not very strong at all, and that one doesn't surprise me. And then we have three more. Here's a strong one: waist and weight at 0.89, waist and arm circumference, and waist and height, hardly any at all. So if I was trying to predict height, waist would have very, very little predictive power. Let's look at these others on below the diagonal and see what we've got here. Well, you recognize these as scatter diagrams. This would be a scatter diagram of weight and arm circumference. And I see that this scatter diagram suggests a linear pattern, probably fairly strong. Now, there is something called a correlation ellipse that's drawn in this pattern. A little bit hard to see here because the dots that are my data points are so close together. Just looking at the ellipse, I think you can see it a little bit better down here. But this is called a correlation ellipse, and the narrower and more stretched out the ellipse is, the stronger the correlation. So this is the correlation of weight with arm circumference. This is the scatter plot for weight, arm circumference, and the correlation ellipse for weight, arm circumference. And I see that the correlation coefficient for weight and arm circumference is 0.89, very strong, and this pattern looks like I've got a very strong correlation coefficient also. In this diagram, you have some control over what this red line is. It's almost the best fit regression line, but I say almost because it's not a straight line, is it? You can see the bending. But this is called a low S line, and low S means local estimated scatter something. Anyway, I don't have that title quite right, but what it means is that the red line, where it is, depends upon the value of the dots locally, not globally, but just locally. And you see the line has got a bit of a bend in it. Now that's something interesting that we may be able to take advantage of a little bit later, because it looks like we could have a really strong linear correlation up to about here, but then change the line and have another strong linear correlation here. So it looks like we've got a linear model with a breakpoint in it. But we'll get to that in a later talk. The red dots are the coordinates, where the coordinates x bar, y bar live. So this is on the horizontal axis, this is x bar, on the vertical axis, y bar. And you remember what x bar and y bar are. X bar would be height, and y bar in this case would be a weight. Well, and we have several more of these. Like here I've got something where I don't see a whole lot of predictive power. Arm circumference is not predicted by height. Well, we knew that from looking at the correlation, and we see the correlation ellipse, which reifies that, tells us again that there's not much correlation there. So there's a lot of information that's packed into this one graphic. The graphic gets overly busy if we've got too many predictors that we're looking at. That being the case, we'd probably want to look at part of them and then look at another part of them. But if we've got 4 or 5 or 6 predictors, this is really a useful graphic. Now let's jump back into our code. we just looked on line 256 at the way we predict the Pierce panel graphics, and I could give you another, just a couple more. I see that this has gone longer than I thought, but I can give you just another couple tips on using Pierce panel graphics. If I wanted to look at just the women, do a Pierce panel graphic, but just for the women, when I name my data new body, I would use subsetting, that's the square brackets, and I would limit to gender equals 0, and 0 is women and 1 is male. So I would limit the data I'm looking at to just data for women, and then I would use weight, arm circumference, height, and waist, and run that again. And where are you? Here you are. And you would need to maybe, I don't know, maybe even print these out and look at them side by side. But it's a different looking graph if I restrict my predictions just to women. And of course, another thing that I could do would be restrict my predictions just to men. And if I was restricting just to men, is all I'd have to do is to change this number to a 1, and then run that again, and I'm predicting just for men. And I thought, being a programmer, I guess from the old days and the old style, this would occur to me. I could just keep this construct, and if I wanted both men and women, instead of having the relation equals 0 or 1, if I'd use a relation less than 2, I would get both men and women. Since men are coded as 0 and women are coded as 1, but both are less than 2, so I would get everybody. So that would be kind of a trick that would maybe just save you a little time or be worth looking at. Well, why don't we try a linear model, and let's predict weight with arm circumference and the waist. Now, the way we do that using the R-base linear model is LM is the model, and then you name the thing you're trying to predict, in this case weight, and the tilde separates the thing being predicted from the predictors. And if I want to use two independent predictors, I just put a plus in between their names. And I'm not naming my data frame on the left, and so I have the data equal new body, the name of my data frame, trailing here. And I'm storing this linear model in WT, weight underscore M, weight model. And after I create the model, I can see features using the summary command. So we'll say summary and run that. And we get some crucial information here. We get a reminder of what we called for, and this was weight predicted by arm circumference and waist, and so that's just a reminder. We look at the residuals. Now, what we're looking for in residuals would be a normal distribution with a mean of 0 and hopefully a small standard deviation. So we get information right here, but we have to interpret the information when we're doing linear regression. So I'm looking at my residuals, and I see that it doesn't give me the mean, but the median, so half the residuals are below negative 0.5. We want the center to be 0, but it's not quite, at least in the sense of median, 0. The center is negative 0.5, which means half the residuals are below 0.5 and half negative 0.5, and half are above, which tells me, the negative just means that the predicted value is less than the observed value, and a positive would be the predicted value is more. Now I can see IQ, but first quartile, 1Q, and 3Q, first and third quartiles, between these two values, we're going to have 50% of our data. So 50% of the predictions are between negative 4.7 and positive 4.3. That's not 50% of the predictions, that's 50% of the error in the predictions. So between negative 4, that would be kilograms, because the data we're using is in the metric system, and positive 4 kilograms. I see that this is, pretty symmetrical. This is just about 0, and these are pretty symmetrical here for the first and third quartile. So that's looking a little bit like residuals are normal. It's also looking a little bit like the standard deviation is probably a little more than what I need. And remember the rule of thumb that says that the range divided by 4 is going to be just about what the standard deviation is. Well, a real quick computation here. This is about negative 20, and this is about positive 28. And so that would be 48 divided by 4. So the standard deviation is about 48 divided by 4 is about 12 kilograms. And that's a pretty big standard deviation. So I guess right away I'm not as happy with the model residuals as I could be. Now we've got more. We've got the intercept and the arm circumference and the waist. The intercept, beta naught, arm circumference, the coefficient would be beta 1, and waist would be beta 2. And these are their values. Well, their values are what they are, but they tell me something. It tells me that, other things being held equal, arm circumference, each unit increase in arm circumference, and this is measured in centimeters, would add 1.95 centimeters, kilograms to the weight, since we're predicting weight. So each unit increase in arm circumference, and a unit there would be a centimeter, gives me just about a 2 kilogram increase in weight. And waist, well, each unit increase in waist, which would be centimeter increase, yields about a little over half a kilogram, which is roughly a pound to the person's weight. Now, that's what these values computed as, and that's the interpretation. But how comfortable are we that these values are really contributing to the model? Well, if we look over here at the p value over on the end, this is the result of a two-sided test. And the two-sided test that the 2e minus 16 goes with is that the intercept is really 0. And this would be the p-value. And remember, if a p-value is less than alpha, then we're going to reject the null hypothesis. The null hypothesis is that the intercept is 0. I have to reject that based upon, this is a t-test, just a test of hypothesis. Now, if the arm circumference has a coefficient that's really 0, that means the arm circumference is of no use in this prediction, in predicting the weight. So if the coefficient of arm circumference is 0, then it doesn't matter what arm circumference is, it won't change the value of the estimator for y. Well, the probability that the null hypothesis, this coefficient being 0, is true, that probability is minuscule, almost vanishing. So I'm going to have to reject the null hypothesis that arm circumference does not contribute to the weight, at least the prediction of weight. And the same for waist. So we've got essentially a 0 here for the p-value. For the hypothesis, waist coefficient is 0. We reject that also. So if the question is the model useful? Broadly, you'd answer that by it's useful if I've got some predictive power, which would mean that one or more of these terms actually have predictive power for weight. Now, there's type 1 and type 2 errors, and so what we're going to have to get at next is what's the likelihood of a type 1 error if I look at these three results, these three p-values, is a way to test simultaneously if all of these terms are zero. If all of these terms are zero, my model has no utility whatsoever. So how would I test all of these are zero simultaneously? Do all three have the same value, 0? Does beta 0 equal beta 1 equal beta 2 equal 0? Well, some of you may recognize that as a null hypothesis for an analysis of variance. And we run an analysis of variance, and in our next lecture I'll show you mathematically that what I'm going to tell you right now is true. If I want to find out if all of these coefficients that you see right here are in fact 0, and this is just statistical noise that makes them look non-zero, if I want to test that, the probability of a type 1 error, if I do it this way using 3 independent t-tests, the probability of a type 1 error grows huge compared to the probably 0.5 that I'd like for it to be. But if I use an ANOVA, I can hold the probability of a type 1 error to the 0.5. That would be my usual choice. R runs a type 1 an analysis of variance for me with a reduced type 1 error of 0.5. And when I run the analysis of variance, the null hypothesis is that all of these coefficients are 0, and the p-value for that hypothesis test is essentially 0. So I have to reject that hypothesis. It looks like the model we've created here has some predictive power. Now, how much of the variability in weight is explained by the variables arm circumference and waist? Well, that's what the adjusted R-squared tells us. And it tells us that 88% of the variability in weight can be explained by just these two variables, arm circumference and waist. So it looks like that's a pretty good model. Now, does any of this tell me it's the best model? No, it does not. And that again is thrown back on us. And so at this point we could pat ourselves on the back a tiny bit, but I think we're going to have to look a little more at what we've got to work with and how this model turned out and see if it can be improved. So there's some other things that we're going to try, but we've gone half an hour already with this video, and so we're going to stop right here. So look for more videos in the near future, and have a good afternoon, evening, morning, day, depending on when you watch this. Thank you for being with me.